All right, take two. Hey guys, we are talking about Chapter 12. Chapter 12 is all about force. And so we're talking this section about Newton's first law and also Newton's second law. And so the question that's asked is, what makes an object speed up, slow down, or change directions? You can think of that example I had in class when someone was standing here with equal forces acting on them. They had a net force of 0, and it wasn't until somebody pulled harder on one side or the other that they accelerated in the direction of that person. And so Newton's first law says that objects change their state of motion only when a net force is applied. In other words, if it's not moving, it's going to continue not moving, or if it is moving, it's going to continue moving in a straight line in that direction, unless some outside force acts on it. This principle is called Newton's first law. I want you to think of an air hockey table. If I put the air hockey puck down on the air hockey table, the puck's weight is pushing it down, the air is pushing it up, and it's going to stay balanced until I push it with one of the air hockey paddles. Then it'll keep going in that direction at that speed until it hits a wall, in which case it'll change directions. That was an outside force. And it will keep going in that direction at that speed until another outside force hits it. So objects change their state of motion only when there's a net force that acts on them. Now, objects tend to maintain their state of motion, and inertia is related to an object's mass. So inertia is the tendency of an object to resist change in motion unless an outside force acts on that object. And because it's related to mass, you can think of a train and a car. A car is fairly easy to cause it to accelerate, to go from stop to go fast, and it's easy to slow it down. You hit the brakes and it goes from fast to slow, and depending on how fast you're going, it's relatively easy to speed up and slow down a car. Now a train, which is much more massive, has much more inertia. If a train is going really fast, it can take several kilometers for that train to stop. If a train is completely stopped, it takes several minutes for that train to get going and to leave the station. Because the train is more massive, has more inertia, and it resists change in motion more. Now, think about your seatbelt. Because inertia is the tendency of an object to resist a change in motion, think of driving a car. If you don't have the seatbelt on, the car stops, your body resists that change in motion, and it flies forward in the seat. Now, it's important to wear a seatbelt because when the car comes to a stop, your seatbelt and the friction between your butt and the seat will provide the unbalanced backward force that's necessary to cause your body to come to a stop when the car comes to a stop quickly. I'll give you a moment to write that down as I've asked you to explain it. And you might want to pause if you're still writing. So, Newton's second law. Question is, what determines how much, where can I put this? Maybe here? What determines how much an object speeds up or slows down? Now, net force is equal to mass times acceleration. The unbalanced force of an object determines how much an object speeds up or slows down. This principle is known as Newton's second law. So, let me hold up the slide for it. I believe it's this one. Net force equals mass times acceleration, or you can write it F equals ma. Now force is measured in newtons. 1 Newton is 1 kilogram times 1 meter per second squared. And when we're talking about labels, it would get very hard to write that down. Every time we wanted to talk about force, we don't want to have to write kilogram times meter per second squared. So instead, we've come up with this thing we call a Newton. And we label it with a big N. Which makes sense because kilogram is a unit of mass, and meters per second squared is the most common unit for acceleration that we've used. So you can just think Newton is a combination of mass and acceleration together. Now, for equal forces, a larger mass accelerates less. Those of you guys in football, you can see that picture I put down there. You can think of, I don't know what it's called, but those, when you're conditioning, those stands that sometimes they'll have that look like a football player and you push against them. If there's nobody on that stand, even though you're pushing as hard as you can, it's going to move a lot easier than when you have a couple big linemen standing on it to hold it down. Now, you might get a better workout if there's a couple big people on it, but pushing with the same amount of force, a larger mass is going to accelerate less. You're pushing really hard, and it's the same amount of force as if there was nobody on it, but large force accelerates less. It's kind of common sense, and it makes sense to you that if a bunch of people jump on it, it's going to be harder to push. It's going to accelerate less even though you have the same amount of strength that you're using. The other principle for this is that if it has an equal mass, greater force is equal to will yield greater acceleration. So in other words, you can see that picture of that Volkswagen Beetle, one person pushing it, it's going to be less acceleration than when lots of people push it. The car's mass is staying the same, but greater force is yielding greater acceleration. And of course, then it makes sense that if you had a really big force on a really light or very not massive, something with very little mass, and a very great force, it's going to move very quickly. Yeah, so that's kind of a combination of those other two phrases. So let's look at one example for calculation just as we wrap up and as we finish. Here's the example. So, zookeepers lift a stretcher that holds a sedated lion, happily sedated and not awake. The total mass of the lion and the stretcher is 175 kilograms, and the upward acceleration of the lion and the stretcher is 0.657 meters per second squared. What force is needed to produce this acceleration of the lion and the stretcher? Now, looking at the board behind me, we're supposed to list our given and unknown. So we know our mass, which is 175 kilograms. And we know our acceleration, which is 0.657 meters per second squared, and we are looking for our force. Step number 2 says write the equation for Newton's second law. So we know force equals mass times acceleration. And finally, we insert our known values into the equation and solve. So force equals 175 kilograms times 0.657 meters per second squared equals, and I flip through my papers to see what it equals. It equals 115. And here's where we look at that definition of newtons. Normally we would label this kilogram meter per second squared, but since that is the definition of a newton, we can label it simply with a capital N for Newton. And that doesn't quite bring us to the end, because now we have one more thing that we need to cover. So, Newton's second law can also be stated as follows. I'll back up for just a second. Newton's second law can also be stated as follows. The acceleration of an object is proportional to the net force on the object and inversely proportional to the object's mass. We can write it like this. Acceleration equals force divided by mass, or A equals F over M. Thank you for watching, and I hope to see you in class.